The metric tensor. Unlocking the mathematical structure of spacetime. Where are we, and what kind of space do we live in? This seemingly simple question has led humanity into the profound mathematical structure of spacetime. And at the very heart of this exploration lies a powerful tool, the metric tensor. Spacetime is the stage upon which our lives unfold and where the universe reveals itself. But understanding this stage intuitively is not enough. According to Einstein's general theory of relativity, gravity is not a conventional force, but rather a curvature of spacetime itself. So, how can we describe and quantify this curvature in a precise and mathematical way? This is where the metric tensor comes into play. The metric tensor is a fundamental mathematical object that defines the structure of spacetime. More specifically, it is responsible for determining the distance between 2 points, in other words, the line element. In flat geometry, we are familiar with the Pythagorean theorem, ds2 equals dx2 plus di2 deciseconds squared equals dx squared plus di squared, as a measure of distance. However, in curved spacetime, this simple equation no longer holds. Instead, we use the metric tensor in the generalized form. ds2 equals gmn dx mu dx nu ds squared equals g underscore mu nu dx caret mu dx caret nu here. gmn g underscore mu nu is the metric tensor. This tensor tells us how space and time behave at every point in spacetime. For instance, near a black hole where gravity is strong, spacetime is intensely curved, time flows more slowly, and distances are perceived differently. All of these phenomena can be described and calculated using the metric tensor. In this sense, the metric tensor acts as the language of the universe, encoding the very shape and structure of space and time. But the metric tensor doesn't just help us calculate distances. In physics, it is also the foundation for constructing other essential mathematical objects, such as the Riemann curvature tensor, the Ricci tensor, and ultimately the Einstein tensor. These objects are key to Einstein's field equations in general relativity, which describe how matter and energy influence the curvature of spacetime. The Einstein field equation, Gmn equals 8 pi t mn g underscore mu nu equals 8 pi t underscore mu nu, connects the geometry of spacetime on the left-hand side via the Einstein tensor Gmn g underscore mu nu with the distribution of matter and energy on the right-hand side via the stress energy tensor Tmn t underscore mu nu. And again, all of this begins with the metric tensor. What's fascinating is that the metric tensor is not fixed, it changes depending on the gravitational field. It takes different forms under different physical conditions. For instance, in flat spacetime, we use the Minkowski metric, commonly applied in special relativity. Near a non-rotating black hole, we use the Schwarzschild metric, while rotating black holes require the Kerr metric. Each of these is a specific form of the metric tensor adapted to the physical context. In this way, the metric tensor becomes an indispensable tool for physicists trying to understand the universe. With it, we can explore the event horizon of black holes, understand gravitational lensing, and even describe the expansion of the universe. Gravitational waves, first observed in 2015, are themselves ripples in spacetime, detectable as changes in the metric tensor. That discovery marked a historical moment where we observed not just matter or energy, but spacetime itself moving. Our daily experience doesn't reveal the true complexity of spacetime. But beneath the surface lies an incredibly intricate and beautiful geometric structure, and the metric tensor is the mathematical key to unlocking it. It's not just used in general relativity, but also plays a central role in modern theoretical physics, including string theory and M-theory, where higher dimensional spacetimes are considered. Another remarkable feature of the metric tensor is its tensorial nature. It preserves its meaning regardless of the coordinate system. This ensures that the laws of physics are the same for all observers, a principle known as general covariance. No matter how we choose to measure or observe the universe, the metric tensor provides a consistent and universal description of reality. To understand the metric tensor is to understand the architecture of the universe. It is more than just an array of numbers. It is a bridge between mathematics and the cosmos, a symbol of humanity's quest to read the language in which nature is written. Einstein's revolutionary idea that gravity is the curvature of spacetime was made possible through the introduction of the metric tensor. In conclusion, the metric tensor is not just a tool for mathematicians or physicists. It is a profound concept that allows us to answer some of the most fundamental questions about our existence. What is space? What is time? What is the shape of the universe? As we seek to decode the hidden patterns of reality, the metric tensor stands as one of our most powerful instruments. It offers not just equations, but insights into black holes, cosmic expansion, gravitational waves, and the very fabric of the universe. Hidden within its mathematical form is a vision of a universe rich in structure, governed by elegant rules, and waiting to be explored.